Dear teacher, my name is Yuan Gao and that is my student Andy. Today I'm gonna talk about the video project task 3. Before the task 3, I write it down the task 1 and task 2. In task 1, I choose a steel bridge near the Flinders Street and measure the length, width and the thickness. In task 2, I give some analysis about this bridge. I draw the shear force diagram and bending moment diagram and some force analysis about this bridge. And in the task 3, I will give more analysis about this bridge. And first, let's start the task 3. There's a little bit introduction about the whole task 3. And in my task 3, I just divided it into two parts. One is for single force and one is for distribution force, and it already shows in VP task 3. And for VP task 2 and for its rule, my force of my force applied to my bridge is 10.69 kilonewton. And I find Young modulus about steel, and the length is 80 meters, the width is 2 meters, and the thickness is 0.4 meter. And first, let's move to the centroid. The centroid in my bridge is located in the middle, located in the point of 910.2. And the next is slope and deflection. I just divided it into two parts. One is 0 meter to 9 meter, and the second is 9 meter to 18 meter. And in this part, we need to find the moment first. The equation of moments is half fx, and we give them the first order integral to find out the slope and the second order integral to find the deflection. And that is the process about my calculation. And for the step, find the C1, C2, C3, C4, and finally we got the slope equation, deflection equation. In here, I just use a letter and equation to show them. I think it's more clear than the number. And the slope about first part is a quarter times fx square minus 81f divided by 4, and the second part of slope is minus quarter of fx square plus 9 times fx minus 243 times f divided by 4. And the deflection is the first part of deflection is fx3 square divided by 12 minus 81 times fx divided by 4. And the second part of deflection is minus fx square 3 square divided by 12 plus 9f x2 square divided by 2 minus 243 times fx divided by 4 and minus 2 times 4 243 times f divided by 2, and our maximum deflection is happening in x equal to 9, and the v max equal to minus 243 times f divided by 2 times of e and I. And the next is a bending stress. In the bending stress, I just choose a point first and then start my calculation. And that is a formula about the bending stress. So in this formula, we should find the m, y, and I, and finally to get out the sigma. And the m is equal to 6 times 5.32, and y equal to 0.1, and I is already here. And finally, we just use a formula to find the sigma is 299.15651 kilopascal. And the shear stress also should follow the formula and find the conditions in the formula. And finally, we follow the formula here to find the tau flow, and the answers of the tau is 7.47891 kilopascal. And next we move to the principal stress. In the principal stress, we use the bending stress and the shear stress we already got to calculation. And the sigma 1 and sigma 2 is in here is 299.34337 kilopascal and minus 0.18686 kilopascal. And the in-plane shear stress is 149.76511 kilopascal. And that is sigma average strength. And next we'll talk about the distribution force. In the distribution force, the N is equal to 10.64 kilonewton per meter, and so the F is equal to N times I times 18 is equal to 191.55 kilonewton. And the central is also located in the middle of the bridge is 910.2, and the slope and deflection will use the same step from the single force, and that is we should find the mx first, and the mx equals to n times a times x divided by 2 minus n times x squared divided by 2, and the first order integration find the slope, and the second order integration find the deflection, and that is the finally slope equation is equals to a quarter times n times I times x squared minus n times x3 squared divided by 6 and minus 243 times n, and the deflection is n times a times x squared x3 squared divided by 12 and minus n times x4 squared divided by 24 and minus 243n, and the maximum deflection also happened in x equal to 9, and the Vmax is already here is times the minus 1096,935 times n divided by 8 EI, and the bending stress just use the same point with the single force, and follow the sigma equal to my divided by I, and in this place the M is a little bit difficult. We should use a bending moment diagram from VB task 2 to find the second square root about the curve and find this equation. And finally, when x equal to 6, find the M is equal to 383.04 kilonewton meter. And finally, find the sigma is 3,589.87816 kilopascal. And the shear stress also follows the formula, the tau, and the tau is equal to 59.8310 kilopascal. And the next, the final is principal stress. Use bending stress and shear stress. We already calculate about distribution force to find the principal stress. The whole process in the hill, the sigma in-plane shear stress and the sigma average stress. And finally is about the conclusion about my video project task 3, and it is appendix, and that's all. Thank you.